And let me share my screen. Okay, here we are. So today we are going to talk about how to model reinforced concrete frame structures in OpenSeas and STKO, but this time using the lump plasticity approach. In the previous webinar, instead, we used the distributed approach. So first, what we'll be doing now is to do a first model. Basically, this one will be used to study the cross-sectional response of a fiber cross-section so that we can get the moment curvature response. Then we will obtain, of course, this will be a moment curvature response for a given axial load. Then we will be using the output of the cross-section analysis to compute the equivalent points for the rotational spring that we will use in the lump plasticity approach using the modified Ibarra-Medina-Kravlinkel model. So we will start from the moment curvature response, we will obtain the moment curvature points, and then we will move to the moment rotation relationships. Then we will be doing another simple model to understand what are the differences between the distributed plasticity approach and the lump plasticity approach. So we will proceed with just one column. We will create 3 of them. The reference one will be the distributed approach that we have seen in the previous webinar. And then we will compare it with 2 kinds of lump plasticity approach. As you know, in OpenSeas, the lump plasticity approach can be achieved in 2 ways. We can either use the beam with hinges model that is available in OpenSeas that basically uses the fiber cross-section, so there is the advantage of taking into account the coupling between the axial load and the bending response. But this nonlinear response will be available only at the 2 lengths, at the 2 ends of the beam, using so this one basically is a lump plasticity approach over a finite length, which is equal to the plastic length. And then there is the most common one, which instead is an elastic section, an elastic beam with 2 zero-length springs at the 2 ends of the beams. This one instead doesn't use any fiber cross-section. It uses a phenomenological constitutive model for each one of the directions, so there is no coupling between the bending responses in the 2 directions, and there is no coupling between the bending response and the axial load. Then we will do a comparison. We will see how to modify the elastic stiff and elastic properties of the inner elements to match the response of the distributed plasticity approach. And finally, we will plug these 2 approaches into the model that we've done in the previous tutorial. So in the previous webinar, we did this very small building here using the distributed approach, and this time we will compare it with the other methods. So we'll distribute it lumped over a finite length unit using the beam with hinges, and of course the lumped with the rotational springs. Okay. Now you will find, tomorrow you will find the recording of this webinar and all these files on our website. So let me close all these models, so we'll start from the beginning. And we will start with the cross-sectional analysis here. So let me do a new model. Okay, so let's start from the very beginning. Perfect. So now we are going to do the analysis of a moment curvature response. This one can be done in STKO, creating a beam element of a unit length, and this element will be subject to a constant state of deformation, so that we can get from the resisting moment and the rotation on the top, we can get the moment curvature response. So let's start by creating a simple geometry. So we go in geometry here, and we draw a line along the x direction. The direction x will be the direction of the axial load. So we start from 0 to 1. We need this one to be a unit length. In this way, rotation and curvatures are the same. Okay, so this is our model, very simple. And then we start with, as usual, we will be doing a monotonic response. We just need the backbone curve for the moment curvature response, so we can create a linear time series for the analysis. We can call it ramp, and we choose time series linear from 0 to 1. Perfect. Now we go with the physical properties. So first, let's create a concrete model. And we use, as usual, the concrete 01. So uniaxial, concrete 01. All the models I will be doing today are in millimeter and newtons. So minus 35 megapascals, minus 0.002, minus 5 megapascal the residual strength, and minus 0.15 the ultimate deformation. So let's do a test. Monotonic. So this is our response in compression. That's fine. We do the same for steel. So let's create a steel model. Uniaxial. Steel and reinforcing steel, and we use the Menegotto Pinto model. Here we'll be using 485 megapascals, then some constants for the shape of the striated curve, 0.925, 0.15, 0 strain hardening, and 206,000 megapascal. Okay, a quick test to make sure everything is fine. Okay, perfect. So we have the steel, and now we can create the fiber cross section. Here we will be using the same fiber cross section we used in the columns of the previous model, the previous webinar. Because in this webinar, we will focus on applying the lump plasticity only on columns. Of course, you can do the same for beams, but since we don't have much time, we will focus on the columns, which, by the way, are those that carry the nonlinearity of the model. So let's add a fiber cross section. And we are going to choose the rectangular fiber section, so it will be easier to input. Let me give a torsional stiffness 4.2 or 15. Then this one was a 500 times 300 model. Rebars are fine, just 3 on top and bottom, and then 2 on the sides. Then we use the rebar material and the concrete material only for the cover, so that the core concrete will be computed automatically for confinement. And now let me change a little bit the stirrups, because in the previous example it was 8 millimeters of diameter, then a spacing of 100 millimeters, and 2 legs in both directions. And here let me give the same strength of the longitudinal bars, and that's fine. So this is our response for the cover, the one that you input before, and this one is the automatically computed confined concrete. So this is fine. And now, of course, we need to create, as you may know, the beam section property. So we have special purpose beam column, beam section property. Call it beam property. And here we choose the standard integration type, Lobato. Now, in this case, we just need one section, theoretically, because this will be a constant state of deformation. However, the Lobato has a minimum of 2 cross sections. If you put 1, you will receive an error from OpenCV. So 2 cross section, and we choose the section we just created. Okay. Now for the element property, here there is a note. Since we are forced to use 2 cross sections here, 2 integration points, make sure in this example to use the displacement-based model, because the displacement-based model will localize in the entire element. while the force-based will localize only in one of the integration points. So the response will not be what we expect. Instead, we want a constant state of deformation over the entire element. So in this example, we choose the displacement being column element in 3D. Okay, so we can just, let me give it a name, the element, and we assign both the physical property and the element property. So we are fine. Now we need boundary conditions. So of course, one of the ends of the beam will be completely fixed. So let's call it fixed node 1. We choose a constraint, a single point constraint, fixity, 3-dimensional, and displacement and rotation, and we fix everything in the first node. So press OK. Let me go to the condition so we can see. So the first node is fixed. Now we need some constraint on the end node, and we call it fix n2. This will be always a single point constraint, a fix, always in 3D and 6 degrees of freedom. But here we just need to fix the, we need to release the x and y. X, we will be doing a moment curvature response about the z-axis. So of course the x should be free to move because we want to keep it in equilibrium with the applied horizontal load, so with applied axial load. The vertical response here in y should be free because of this one will be the deflection due to bending. Instead, we fix the out of plane translation and this to rotation here. So we do a uniaxial bending moment response. And of course, we select the target node and we press OK. Perfect. Now, the third boundary condition is the axial load on the second node. So let's call it axial. Now, why are we putting an axial load? As you know, moment curvature response depends on the axial load. And since we need to create an equivalent, the equivalent properties for a spring, and in OpenC's, the lump plasticity approach with springs is uncoupled from the axial load, we need to compute the proper response for the axial load that we expect. And in our model, in the model that we will be doing at the end of the webinar, the axial load at the end of the gravity analysis will be 20 kilonewtons on each column. So here we use a force, another force of 20 kilonewton. In this case, in the x direction, because this is the direction of the beam in this example. So 20,000 in this node. Okay. Well, actually, I drew it on the wrong direction. Let me rotate it. Let me go to geometry. I was on the wrong work plane, so I can rotate it now. Okay. So perfect. That's fine. Let me go back in condition. Okay, now here we have the axial load. We don't need the local axis, they are fine. Perfect. So the next boundary condition that we need instead is the applied curvature. Now, of course, since this one is a unit length beam, we can apply a rotation at the end node, and this will be equal to the curvature that we will obtain due to the fact that this one is a unit length beam. So let's call it key Z. And this time this will be a load, but an imposed displacement, which is equivalent in this case to the curvature. So once again in 3D and 6 degrees of freedom, and we will fix only the rotation about the z-axis, and we will push up to 0.005. In this case, this is a curvature. So let me select this one, and let me press OK. Okay, so basically now we have the fixities, the actual load for the first analysis steps, and then the applied curvature. Now, of course, we start creating all the analysis steps. So the first one is the recorder. Let's call it results. We need displacement, rotations, reaction force and moments. And then if you want to see the fibers, it's fine. You can see the fiber stress and strains just for visual purposes. Okay. Now we need to apply the boundary conditions. So add constraints, pattern, add pattern, constraint pattern. And in this case, we have two single point constraints for the two end nodes. Fix N1 and fix N2. Okay. Then we need to apply the vertical load. Axial load. Well, in this case, it is horizontal, but it is simulating the axial load. Pattern, add load pattern. We choose the ramp. Okay, and the load is not a load, so we place it in this vector, and we choose action. Perfect. Now we can create the first analysis, the load controlled analysis. So analyze actual load. You go under analysis, analysis command. It is a static. We cannot use the plane constraints because we are applying an imposed displacement, so we choose the transformation in this case. This is fine. Since the model is very small, we can choose a full general solver. We don't need a sparse one. Okay, Newton is fine. We check the normal unbalance is fine. We want to see all the iterations, so we see if something is going wrong. And 10 steps is fine in load control, because by the way, this is just for axial load. And then, of course, we want to reset the 10 step to 0, so we can use the same ramp for the applied curvature. So this is fine, okay. Now we need to add the applied curvature. So apply curvature, and this one will be a pattern, add pattern, load pattern. It is a monotonic response, so we use the ramp. I think we have a question. Let me see. Okay. And the curvature is a single point constraint in this case. So we place the applied curvature here, key Z. Okay. Okay. Perfect. And now we just need to conduct the last analysis, which is the moment curvature analysis. So let me copy this one because it will be very similar. So clone and edit it. Analyze moment curvature. This is fine. Transformation method, full general Newton is fine, but we are going to use the Newton with lens search. It will be better for convergency. Then the normal balance test is fine. 1 to the minus 4. Actually, in this case, I think I was using a Krylov Newton, which was slightly better due to softening. Okay. Normal balance is fine. Let me increase a little bit the number of iterations. And this time it will still be a load control because we apply a curvature here. Otherwise, we could have applied a unit moment, and then we need, of course, a displacement control, but it is equivalent in this example. So we will be doing 1,000 steps, and the lambda so will be 1 divided by 1,000. So at the end of the analysis, we reach the load multiplier of 1. We don't need to reset the time step to 0 because now this is the last step. So let's press OK. And of course, we need to mesh it. We just need the default one element discretization, so we build the mesh. Now let me save this file before running the analysis. create a folder here, and this one will be the moment curvature. Okay, save it, and let me run the analysis. Okay, let's wait a few seconds. Okay, the analysis is finished. Okay, let me just show you the output, and then we will go soon to the Excel file to do the computation. So let me open this file, moment curvature. Okay, so this is our section. If you want, you can see the fibers just to see what's going on in the beam. Let's switch off the steel rebar so we can see the stresses. So this is what we expect, of course. Now let me switch off the nodes so that we can select the top node, these two. So this one will be the end node, because from this node we will extract the moment curvature response. Now, as I said, since I applied a rotation on this node, at the same node I have the reaction force, which is actually equal to the applied moment. So we need to extract a chart from nodes. Next, we need to do it for the second stage, which is the moment curvature stage. And we want to plot the rotation about the z-axis against the resisting reaction moment about the z-axis. Now, of course, here it is the rotation, but as I said, it is equivalent to the curvature because this one is a unit length. So next, the node is already selected. Next, and call it moment curvature response. Okay, so this is our moment curvature. Now, of course, you can go here, copy paste these values. You can go to Excel. I already did it, so you can find this file there. Now, what we want to do actually is to use this moment curvature. As I said, this one is the moment curvature response of that section for a level of axial load equal to 20 kilonewtons. Now, basically, what I did is simply a fitting of 4 points used for the Medina-Kravinkler rotational spring. So we had the same initial stiffness, then I took a point here, the peak point at this point, and then the residual strength, okay? Now these ones are values taken from the moment curvature response. So actually, these values here are curvatures. Now, as you know, when we will go in the lump plasticity approach, the rotational springs should be moment versus rotation, okay? In our model, we use a plastic hinge of 150 millimeters. Why? I will show you later, but when we choose this is just for the sake of this example, when we choose the beam element with the Lobato integration scheme, the bottom Gauss point has exactly this characteristic length because the weight of the Gauss point is 0.05 times the length of the beam, which is 3 meters, give us this 150 millimeters. So we will use the same to convert the rotations into curvatures here. However, we do not convert the first one because we want to make the rotational spring, let's say 2 units, order of magnitude stiffer than the elastic member. Because actually the rotational stiffness, the rotational spring should only represent the plastic part. So in theory, this one should be rigid, but of course it cannot be, otherwise you have numerical problems. So in this case, we just keep it 100 times stiffer than the elastic response of the beam, okay? So basically here you have the same points used for the same parameters taken from the moment curvature and moved to the rotation field from curvature, okay? So simply multiplying, for example, for the 2 plastic rotation, we take the curvature and we multiply it by the plastic length. And instead, for the hardening ratio, we need to divide it by the plastic length, because of course we are stretching our curve here. So we need to do the opposite, okay? And then we choose the residual strength as 1.05, the elastic strength. Perfect. So these are the values that we are going to use in the Medina-Krawinkler model. Okay. So now, basically, you have your fiber section response. We converted it into a Medina-Krawinkler model. So now, before applying all these modifications to the building that we have done in the previous example, in the previous webinar, we will do a quick test on 3 columns. Okay. So let me save this one, and let's create a new model. So what we will obtain, just to summarize, let me close it. What we are going to obtain is this comparison. Single column results, okay, these 3 columns here. And we are going to see how to make the beam with hinges and the rotational spring lamp plasticity approach equal to the distributed one. Okay. So let me remove this. Let me create a new file. Okay. So back to the preprocessor. Geometry, we need a 3 meters high column. So let me move to the front view. Okay, and start here. 3 meters in this direction, so 3000. Okay. I can reduce the grid size. Okay. So this is our first column. Now we are going to do the same for the same section we have done before. So I will go a little bit faster because I already explained the material properties. So as usual, I create a definition here. Or actually, in order not to waste time, let me start from a file that I already done, so we do not waste too much time here. Okay, let me start from this one. You will have this file, okay? So we'll start from this, okay? And I will remove these 2 columns. I will be doing them later. So this one will be the column for the distributed approach, okay? So as usual, as I did before, I have a linear time series. Then we have the same concrete we did in the previous example. Same for the steel, okay? And same for the fiber column. The same things we created in the cross-sectional analysis. Then we have the column property for the distributed approach. So Lobato, 5 integration points, all of them has the same fiber cross-section. Now these ones, we are going to create them later because we need them for the lamp plasticity approach. I will explain you step by step. Let me remove them. Okay, we just need one element in this step, which is the force-based beam column. And now for the conditions, we have, of course, a fix at the base. Everything is fixed at the base. Then we have a vertical load as before on top of the beam in the z direction of 20 kilonewtons. And then we have an horizontal load, which in this case is an applied displacement of 15 centimeters, okay? Always in this point. And of course, here we have the usual 10 steps. So recorder, a constraint, where we have in this case, we just need this one, of course. I fix it at the base, okay? And then we have the vertical load, just one in the load vector, okay? So the vertical load on top of the beam, of course. Then we have the vertical analysis, same parameters we used in the previous analysis of the cross section. Then, of course, we add the horizontal load, which in this case is a single point constraint, as usual. And of course, the horizontal analysis. Here you see all the settings. Okay. So let's first run this example. This is the reference one. The reference example, we will try. Oh, let me save it with another name. Okay, this is fine. File save as. Let me save it here in example. We create another folder. single column. I will mesh it, just one element. So build mesh, and we can analyze it. So let's wait a few seconds. And here we will construct the response of the reference distributed approach. Perfect. So let's go to the post processor. Open the example, single column result. Okay, I remove the deformed shape and I create a beam shell fiber color map. I switch on the nodes. Let me remove the grid, we don't need it. Okay. So now we'll select the top node because we applied an imposed displacement here, so we can get displacement versus reaction force here. So extract data on nodes, stage number 2, displacement in the x direction versus reaction force in the x direction. And we can call it displacement force distributed. Okay, this is our reference model, perfect. If you want to see what's going on in the fiber cross section, we are going to plot the strain so you can see here the localization. So the plastic hinge only happens at the bottom Gauss point. This is because this is a fiber, a force-based model, so localization happens only in one integration point, and this is fine. Now we're going to do the same with the lump plasticity approach, first using the beam with hinges model. So we use lump plasticity approach, but taking advantage of the fiber cross-section. And then we will do the same with the spring-based lump plasticity approach. So back to the preprocessor, go to geometry, and we can copy this geometry here. Okay, let me copy it, let's say 2 meters in this direction. Okay, now this one will be the one for the beam with hinges. So of course here we need to orient this cross section. So let me select this one and I drag and drop the local axis because the local axis was already assigned to this element. Okay, perfect. Now they are all aligned. Now you will see a slight difference here, but it is not important. Let me just switch off this. One element is pointing in the up direction, one in the downward direction. In these two elements, there is no difference. You will see a slight difference in the next element, in the one with the springs, but only in terms of the sign of the result. So we'll show it later. In any case, if you want to make all the elements point in the same direction, you have the reverse command. So for example, in this case, I click reverse, and I want to select the geometries whose local direction should be reversed. And in this case, this one. Right click, and of course now it is pointing in on the other side. So this is fine. Let me switch on the visualization of faces. Perfect. Now we need to change a few things here in the physical properties to make the modification. Now, of course, before doing this, let me transport all the boundary conditions from this element to the other. So the fixed base was only applied here. Now we want to apply it also at this node. Okay. Same thing for the vertical load, also to this node. And same for the horizontal load, also to this node here. So this is fine. All the analysis steps do not need to be modified. We just need to do a slight modification here. So the first thing, we need to create an elastic section that will be used for the inner part of this lump plasticity model. So let's call it elastic interior beam. So we choose section elastic. Now let me create the cross section. It will be a box shape. Sorry, box, and it will be 300 and 500 base. Okay, here you have the sectional properties. Fine. Now I will do a mistake here. I will start using the elastic properties of the concrete as it is. So the full elastic, the full Young modulus of the concrete. So 35,000, and the G was about 15,000. Okay. Now you will see that using the elastic properties, of course, you don't take into account that the inner part in the distributed approach is already cracked, because the zero length, by the way, the concrete 01 does not have any tensile strength. So this one is a mistake. Now, just to see what happens, let's keep it like this, and then we will correct it, okay? So we have the elastic interior beam. We have the fiber cross-section for the two ends. So we just need to create another beam section property. Now we can clone it, and we change the name. In this case, it is not distributed, but it is lumped finite length. Okay. Now, as you know, in OpenSys there was that command which was called beam with hinges. Now, that was an old command. In the new version of OpenSys, the beam with hinges is not actually a new element. It's just a force-based element with a different integration scheme. So if you want to create the beam with hinges model, you still need a beam section property. The only thing that you have to change is, instead of using standard integration types, you need to go here and choose hinge integration types. And then you use the default. Now, if you read the paper by Professor Scott, there is an explanation about all these different integration methods. So the hinge midpoint, hinge radau modified, or the hinge endpoint. Now, by default, the old beam with hinges command was using the hinge radau. Okay? So if you need details about how these integration types work, you can see the reference paper by Professor Scott. So when we choose hinge and hinge radau here, we can choose the cross-section tag for the I and J end, as well as the plastic hinge length at both sides, and then the elastic section in the middle. Of course, this one does not need to be elastic. It can be also nonlinear, but in our case, we will be using the elastic one. So in both ends, we will use the column fiber, so nonlinear column fiber. And the plastic hinge length is 150, as we said before. And then for the elastic section tag, we choose the elastic interior beam. Okay? So that's all. This is all you need to create a lump plasticity approach using the fiber section. So lump plasticity over a finite length of the plastic hinge. So okay, we select this line and we drag and drop the lump element. For the lump, actually, this is the lump property. As you can see, it is different. And here you can see, I don't know if you see it, let me switch off. Okay, here you can see the representation of the finite length of the plastic hinge. Okay, and then this one in the middle is the elastic section. Perfect. Now, of course, we need to change also the, well, actually, no, in this case, we don't need to change the element property, because as I said before, the element is still a force-based beam column. So it is fine to keep it like this. So we don't need to change any element, just the physical properties. And you're done. Now, let me run this analysis. Save it, mesh it, and now you will see a problem here. Let's run it. You will see that the responses do not match. In particularly, this element will be stiffer. Of course, because let me reload this one. Okay, so we have the second element. And we are going to extract the data also for this one. So let me select this top node, only the node. Okay, so extract on node. Next, stage number 2, displacement along the x direction versus reaction force in the x direction. Next, is fine. Then we call it UF lump finite length. We don't want to create a chart because we already have the old chart. We will superimpose the new chart data on this chart here. So finish. We go here, and we add the finite length result. Okay, now as you can see, the shape is pretty much the same, but the stiffness is wrong. As I said, of course, this happens because in this distributed approach, all the entire element here is nonlinear. So here we are using actually a second bending stiffness because, of course, the concrete does not have any strength in the tensile response, at least in this model. But in this case, we use the full Young modulus. So, of course, there are many equations to compute the equivalent Young modulus based on the amount of axial load and depending on the national code that you use. Now, in this example, the axial load is very low, and we found that 35% of the Young modulus was fine. So we go here, we modify the interior response. Let's call it 35%. 35. And it was 12,000 and 5,000 here. Okay, this one basically takes into account the fact that concrete is not resisting also in tension. So let's save it, run the analysis, and we'll see the modification due to this change. Okay, now if you have the new version, as you can see here, the charts are linked to the database. This means that I just need to reload the database, and I will see the changes in my results. Also here, as you can see now, they perfectly fit. Okay, and of course, if you want to see what's going on here, the localization is the same, and it happens only at the bottom section. So now here, basically, you created a lump plasticity approach using the fiber cross-section. So basically, you have the advantage of a fiber cross-section that has the interaction between bending in the two direction and the interaction between bending and axial load. And of course, you have the advantage of a faster computation because the interior element is just an elastic section, so it does not to integrate its response in Gauss points. Then, of course, the cross sections here have a certain cost, so you can make it even faster using a spring-based lump plasticity approach. But however, with the springs, you lose the coupling between the two bending moments and the coupling between the bending response and the axial response. So this is what we are going to do in the next step. And for this, we will need the parameters for the rotational spring. So as I did before, let me go to geometry and copy. We will copy this element here. Okay. Once again, I want to assign the local axis. So they match drag and drop local axis here. Perfect. Also in this case, since when you model it, basically the CAD environment decides the direction of the element. Now in this case, the direction is pointing downward. Now it is not a problem in terms of global response. The response will be the same, of course. But if we leave it as it is now, the sign of the curvature here will be the opposite. Okay, so it will be a negative curvature instead of a positive curvature. It's not a problem because the global response is fine, but it is better if you align all the elements, so at least the sign convention is the same for everyone. So we go in reverse, we select this one, so it points upward as the others. Okay, now we don't need any more the local axis. Let's go in property. And now we need to do some change here to make this one spring-based. Now, of course, the first thing that we need is to create uniaxial models for the springs. Now, in this case, we are going to add a rotational spring only about the global y direction or local z direction, because this one is the z direction in local coordinates, sorry. And of course, we need a stiff material for all the others degrees of freedom. Why a stiff material? We can use an equal DOF because in this case, in this very specific example, the beam is oriented along the global axis. So a multi-point constraint like an equal DOF works in global axis. But the problem is that in the general case, this beam or this column element is not necessarily aligned with the global axis. It can be skewed. Now, in this case, you cannot use the multi-point constraints because they are globally aligned. So that's why in STKO we use a stiff material instead of the kinematic constraint. So let's first create a stiff material and don't make it too stiff. Now in this example, it is fine to use 1 to the power of 13. So let's call it stiff. Uniaxial, some standard uniaxial material elastic, and we choose 10 to the power of 13. Okay, so this one will be the stiff material. Then we need to create a modified Ibarra Medina Kravinkler. So let's call it M rotation spring uniaxial material. So we go under model, materials, uniaxial, other uniaxial materials, and we choose the modified Ibarra Medina Kravinkler with pinching. Actually, it is not important now because we are not going to do cyclic analysis. So here you have on the Excel you have all the parameters. So you have all the initial stiffness based on the results that we have here, and then all the moment points here and all the rotation points. Okay. So let me do it real quick. So it's 3.93 to the power of 13. Then here you have the hardening ratio. The hardening ratio, as I told you, is this one computed from the moment curvature response. And of course, this one is the modified one for the moment rotation. So 1.89 to the minus 4. So 1.89 e minus 4. And same thing for the negative direction because the cross section is symmetric. So now the moment needs a sign. So it's 3.3 e power of 8, and the same with the opposite sign in the negative side. This one is the yield strength, so the first one, this one. Then we have the peak strength, but the peak strength cannot be directly specified. Instead, we specify it through the hardening ratio. Of course, so as you can see here, the hardening ratio is computed in such a way that you obtain this peak moment. Okay. Now here we have some parameters for the cyclic response. They are not important, so let me just fill them. And 0.1 for the pinching. Then all these others, we leave it as they are. And then we need the plastic rotations. So this one is the first plastic rotation, 579. Same thing for the negative side. And then this one is the final one, 5.25, 0.525. And then the residual ratio. Actually, this one should be a number which is less than 1. But in this response, as you can see, the residual strength in this point is higher than the elastic strength. So it is actually 1.05, slightly higher. So let me put 1.05 and also in the negative side. And then the ultimate rotation. Actually, we don't want an ultimate rotation. We don't want the curve to drop. So we assign a very large value. So it will go as a plateau. Okay, we don't need anything else. Let's do a simple test, monotonic test to see if it works. 0.1. See. Okay, this is our response that basically matches this one. Okay. So perfect. So now we have a stiff material and the spring material. So we can create the zero length material now. So let me go here and call it moment rotation, zero length material, actually. So this is the material, then we will create the element. We go under special purpose, and we choose the zero length material. Okay, now we need to specify the size and the number of degrees of freedom. Now we use all the directions, so all the degrees of freedom. Remember that in this case, we will be using an element in STKO. Okay, let me first explain something before doing this. As you noticed, in all these models, I just drawn a line, so 2 nodes per frame member. But you may say, okay, but in OpenSys, if I want to create springs, I need 4 nodes actually. 2 nodes for the beam, and then the remaining nodes to connect them with the beam nodes and to assign a rotational spring. So I actually need 4 nodes. And this is very cumbersome because imagine that for every frame, you need to create 4 nodes and to connect the element with the exterior nodes through a zero length element. Now in STKO, we created the hinged beam, which is basically a compound element that basically allows you to create a single element with 2 nodes in STKO. But STKO behind the scenes will directly create the exterior nodes for you. So you don't need to create elements separated, okay? So that's why I created only a single line with 2 nodes. So perfect. Now let me create this physical property for the hinged beam. Or actually before for the zero length. So moment rotation, zero length. And another advantage of using the hinged beam in STKO is that STKO will automatically create the zero lengths and will assign the local orientation of the beams. Now in this case, they are globally aligned. But imagine if you want to create hinged beam in a skew direction, STKO will do it for you. So it will be extremely easier. Why I say this? Because when you have to create the zero length material model for the hinged beam, you need to take into account that this direction are the local direction of the beam, not the global directions, okay? So I will use all of them. Yes, all of them. Then the Z local axis is the one that we will be used for the rotational spring. So only here we will use the moment rotation spring. That's why it is about the local z-axis, because actually this one is the global y-axis. But in this case, for the hinged beam, this one should be considered as local directions. So all the other instead are continuous, so we use the stiff material. So stiff also here. Don't forget to put some material here, because if you leave it as 0 or none, it means a complete release. So this is fine if you want to create a release, but if you want to make it continuous, use a stiff material, okay? So stiff. Basically, continuous in all the degrees of freedom, and a plastic hinge about the local z-axis. Fine. So now we have the material for the zero length. We already have the elastic interior beam that we used for the lumped plasticity with finite length. So we have all the materials that we need to create this assembly here. And that's why we can use the hinged beam that we have in STKO. You can find it under special purpose hinged beam physical property. This is not something that is in OpenSys, as I said, because this one is just is an automatism in STKO that basically will create automatically an element, will disconnect the element nodes from the nodes that you created, and will place a zero length there. So for the interior material model, we just want the elastic interior beam as we did before, and then we assign a zero length, the one that we just created, at both sides. Okay, so we have 2 plastic hinges on bottom and on top. Okay, so we can select this line here, and we drag and drop this beam. As you can see, the representation in STKO is basically the same beam that we have here with a small gap. Now this gap is just a symbol, okay? So its length is not important, it's just a percentage of the entire length, just to allows you to understand that here we have rotational springs. So nothing physical, it's just a symbol. Now, of course, as I said, this element uses the force based element. So that's why we didn't create another element. Now, in this case, we need to create another element. First, we need to create an element for the zero length. So zero length element. And this is pretty straightforward. We go under zero length, we choose the zero length. We just need to specify if we are in 3D or 2D. So that's all. But we do not directly assign it to anything because here we didn't create any spring. Okay? We just need to create now this compound hinged beam. So let's call it hinged element. We go under special purpose, hinged beam. And the hinged beam says, okay, give me the element for the interior beam and give me the element for the two zero lengths. And in this case, we just used a plain, simple zero length element. Okay, this is fine. And this is what we're going to assign to this element here. Okay, perfectly. Now, basically, we are done. Let me see if I copied the boundary condition. No, so I need to copy the boundary conditions. So we edit the fix and we apply it on this bottom node as well. Same thing for the vertical load. And same thing for the horizontal imposed displacement here. Okay, now basically we hope this one will give us the same response. And it will give us the same response basically because the correction of the elastic stiffness is already included here. Okay. So just mesh it. As you can see here, we just have in the mesh inside STKO, we just have 3 elements, and of course this is pretty straightforward, and 6 nodes. So at this point, we don't have any spring here. We just have 6 nodes and 3 elements, while we was expecting at least another node here and another node here, and here 3 elements, the element and the 2 zero lengths. Actually, they will be created automatically when STKO writes the TCOD file. So this is very convenient when you have to do a very large structure because you can create a continuous frame structure and then you apply the hinged beam and STKO will separate them for you. Okay. So let's run the analysis. But oh, this is fine. I can use the same results. Oh, yes, I forgot something here. As you can see here, I have an error. Let me show you. Basically, here I made a mistake. I used in the hinged beam an elastic section as a property here. But then I used a force-based element here, the beam element, as an element, and they are incompatible because the elastic cross-section can be used only with the elastic beam section. So let me do this fix here. Elastic element, and we go under beam column elements, and we choose the elastic beam column, okay, in 3D. That's fine. Now we move it before the hinged beam, then we edit the hinged beam and we say, okay, instead of the force beam column element, we use the elastic element so that it is compatible with the elastic cross section. Let's save it and run the analysis. Okay, let's wait a few seconds. Now we go to the post processor, and as we did before, we can just update this one. Okay, so that we have also the other beam. Of course, here we don't have fibers, so you cannot see fibers there. Okay, we can just see the fibers on the other 2 elements. Okay, so now let me export the chart data also for this one. So we select. Now, of course, if you go here you understand where is the difference. If I click here, it's okay, what you want to select? The node number 6, which is the one created in STKO, or the node number 8. Now, this one is the extra node created by STKO, so that between node 8 and node 7 and node 6, there is the zero length. Now, in this case, we want to select the node that we had in STKO because that is the node in which apply the imposed displacement. So we select this one, we go in extract chart data, and we do the same we did for the other elements. So stage number 2, and we want to extract displacement along the x direction versus the reaction force in the x direction. Next, next, and then we call it lamp 0 length. Okay, we didn't create another chart because we are going to use this one, and we are going to add the lamp 0 length. Okay, so this is the output of our response. So as you can see, they match. But of course, this is much more simplified because it's only it's a multilinear instead of a continuous response. But as you can see, it matches pretty well. So this is how basically you can handle lamp plasticity. Basically, you have to take into account the length, the finite length of the plastic hinge. Now of course, the three model coincide, but just because we created the material parameters for the modified Ibarra-Medina-Cravinkler based on the moment curvature of these cross sections at the exact same level of the axial load. Now, of course, if we change the axial load, this one will not depend on that. Okay, while this one will do take into account the axial load. So this is fine. Now basically we can do the same thing now in the structure to see that basically it's very simple. The same modification we did to the column are the same modification that we need to do on the structure level. So it is quite simple. That's simply because we don't need to create manually all the springs. This is very advantageous. I think we have a question. Okay, so what is the difference between the elastic beam and the elastic force beam column element? The only difference is that the elastic beam is a displacement-based element, while this one is a force-based element. Now, in our case, at least in the elastic response with a constant cross-section, there is no difference because they are elastic and they have the same material properties all along the elements. So basically, they are the same. They don't give any different result. There is a difference if you want to use an elastic element with different cross-section. Then the elastic force beam column will give you the exact response, while this one will only impose a compatibility condition instead of an equilibrium condition. But in our case, it is the same. Then there is a difference in the way they accept the material model. So the elastic beam column accepts an elastic cross-section, while the elastic force beam column needs also the integration scheme. So that's why there was that error before. Okay, so whenever you have to do elastic things with a constant cross-section, it's easier to use the elastic beam column because you can just use the elastic cross-section. Otherwise, if you want to use the force beam column, you also need to specify the integration scheme and other stuff. But this is a minor difference in this case. Okay, let me see if we have other questions. Okay, so now we can go to the final example, and we will see how to apply these modifications here that we did on the single column to the entire model. And we will see that basically there is no difference. We can do the same thing that we did for the single column. So it's very simple. Let me just create a new post-processing file here. And I want to save this one. And I will start with these elements. So instead of creating that table from the beginning, otherwise we waste time, you can start with the building distributed example that I will send you, that you will find on the website. And then we will do slight modification to create the others. So the lamp with finite length and the lamp with zero length. So we can start with this one. And we save it in a different location so we can modify it. Single column moment curvature, and this one we can call it building. This one is the building distributed. Okay. And here it is. Basically, this one is the same example that we did on the previous webinar. If you remember, in that webinar, we first started with a plain structure, so just the columns and the top beams, the rigid diaphragm. Then we started applying some modifications. So for example, we have seen the problem of using a fiber cross-section in the beams together with the rigid diaphragm. We have seen that the beams develops an axial load, which is unphysical, and that's why we used the end releases here to reduce or to nullify the axial load on the beams. And then I showed you how to use a nonlinear shear using the section aggregator, and then how to create beam column joints. Now in this example, I will just keep the end releases here, but not the shear and the beam column joints, because in those examples, the shear was dominating, the shear failure was dominating the bending failure, and the joint failure was dominating the shear failure. Now in this example, we are focusing on the bending failure. That's why we want to see it. So we do not include any shear or joint failure. Okay, so just the frame model we did in the previous webinar. Okay, so just to summarize, we have the structure here in the geometry. We have a master node for the rigid diaphragm. Then we have an interaction for the rigid diaphragm. A linear time series, which is used both for the vertical loads. Let me switch off the local axis, which is used both for the vertical loads and for the horizontal load applied on the master node. And then we have all these physical properties. Now let me start little by little, because here we have, okay, here we start, this is where you can start. So basically, if you start from this model, what you have? You have a uniaxial material model, which is the stiff, the same one that we used before in the column example. This stiff material model will be used every time we need an hinge, and we need to keep the continuity in 1 degree of freedom. Okay. On the contrary, there is the soft one, which is actually useless. It's a zero stiffness model in cases in which we want to create a release. And in this example, in fact, we want to create a release on the beams. Then, of course, we have the same concrete we did before. Okay, same steel and same column fiber. Okay, the one with the confinement. Then, of course, we have the column property for the distributed approach, which is the standard Lobato with 5 integration points. Then, in the previous webinar, we created the same beam fiber, but without the confinement for the beams, just a slight difference in the rebar layout. Then we have the same beam property for the top beams, so always a force-based beam element, Lobato scheme, 5 integration points. And then, as I explained in the previous webinar, we created these zero lengths, the continuous one for the initial point of the beam, and the axial release, which is basically using the stiff material everywhere, but in the axial direction, so that these beams can slide in the axial direction and do not develop any axial load due to the constraint given by the rigid diaphragm. And then, of course, here you have the hinged beam. In this case, this hinged beam is not used to create a plastic hinge. It's just used to create a release. So it is a multi-purpose element. Then, of course, we have the force-based beam column element for the columns here, and the zero-length element and the beam element plus hinges for the end releases at the top beams. Okay. Then, of course, all the boundary conditions, so the fixed at the base, all the base nodes were fixed in all the directions. Then we have a fixity on the master node, because the master node is only connected in 3 degrees of freedom. We need to fix the other 3 in the other plane direction, of course. Then we have a multi-point constraint for the rigid diaphragm assigned to the interaction. Okay. Then we have the vertical load in such a way that each column has 20 kilonewtons. And then the horizontal unit force, because in this case we don't want to apply a and impose displacement. Instead, in this case, we apply a unit force and then we do a displacement control analysis instead of a load control one. And then we have all the typical steps. So the recorder, we add the constraint, we add the vertical load, then we do a vertical analysis, same parameters we used before. When we finish the vertical analysis, we can apply the horizontal load, and then we do a displacement control, okay? So this is the file we can start from. So let's run the analysis just to have the reference result. Okay, and of course, just let me stop it. I gave it different names for the recorder because we want to keep different results. Then I will show you how you can compare different results in the same post-processing session. So for this model, we call the result building distributed, okay? So let me run the analysis. Let's wait a couple of seconds. Okay, so the first analysis is fine. Let me save this model, go to the post-processor, and we open the first database. So we go in example, this time in building, and we have building distributed, okay? Let me get rid of the form shape. Instead, I want to see the beam shell fiber color map, and I want to see these strains. So as you can see, localization happening only at the base columns, actually at the base Gauss point, okay? So this is our first model. This is fine. Let me show the node so that we can extract the displays, the pushover curve of this floor here. So extract chart data. We want to accept a result on node. Next, stage number 2, which is the pushover analysis. And in this case, we want to extract the horizontal displacement versus the pseudo time steps. Because since we used a unit force here, the pseudo time step is actually the load multiplier. So it is equal to the inverse of the base reaction. So next, and we can call it UF distributed. Now in this case, we want to create a chart because this is the first one. Of course, now you have the displacement here and the time or the load multiplier in the other direction, okay? Perfect. Now, let's go back to the preprocessor. We are going to save this one with a different name, and we are going to use the lumped approach with the finite length. So save as building lumped finite length. In the same folder is fine. Okay. And before doing any modification, I want to translate this one so that the results will not be in the same position, will be slightly translated, so that we can overlap the different plots. You will see later. So let's go to geometry and choose move. I select the entire geometry and I move it so that it does not overlap with the previous result. So let's put it here. Okay. Now let's check that after this modification, the local axis didn't change. Now in this case, as you can see, in this column is pointing downward. As you know, it's easy to fix, even though it is not mandatory. Okay, so it is pointing upward now. This is fine. Okay, now we do the same modification we did before to convert this distributed model into a lumped one with finite length. So if we remember, we just need to create an elastic section. So elastic section for the interior. And as you remember, we want to keep only the 35% of the Young modulus, which was fine in this example. So we go under section elastic. We choose the shape as we did in the previous column example. So a box, which is 300 times 500. Okay. And the reduced material properties for concrete, which was 12,000 and 5,000. Okay. So this is the elastic section. Now, since we have to use it inside the column property, I'm going to move it upward because, of course, we cannot reference a property here. We cannot reference a property which has an higher tag because in the history it has not been created yet. So we move it before, okay? And we are fine now. We just need to convert this one. So as you can see, using the lumped plasticity with finite length is very easy. We just need to create an elastic section. The fiber cross section is already there. So we take the beam section property and we modify. Instead of being a standard integration type, it needs a hinge integration type. The default one is fine. And then we choose for the two hinges the column fiber, for the two ends, I and J. Plastic hinge length was 150 units, millimeters, sorry. And the elastic section in the middle. Okay, so this is fine. We don't even need to change the element property. We just need to change this one. So let's go to property, and here you can see a different representation. So you have the representation of the plastic hinge. Okay. So save it. We need to remesh it because as we moved the geometry has changed, has cleaned this mesh. So we need to regenerate the mesh, and we can analyze it. Oh, I made a mistake. Fortunately, I remembered. I need to change the name, otherwise it will overlap with the previous results. Instead, we want to keep separate results, so we call it built-in lamp finite length. Okay. Now we can run the analysis. Now, same location, because now it has a different name. Okay. Now, probably I didn't show in any previous webinar that actually when you are in the post-processing section, you do not, it's not necessary that you post-process only one database at a time. In fact, you may have many databases. Now, in this case, for example, I have the building distributed database, but I can load another database. So open database, and I choose the other one, lump finite length. So I open it, now I have two databases, and that's why we created the plot groups. This is why probably many of you have been wondering, why do we need plot groups? Well, this is one case, when you want to compare different results. So now we have the fiber cross-section for the database number one, and then we can create another plot, and in this case, still a fiber cross-section, which in this case, by default, is using the last database, but you can change it, okay? In this case, we want the second database. Second stage, this is fine, I want to show the same results, so fiber strain. Okay, so we can synchronize them now. And as you can see, they are perfectly synchronized in this way. And this is the reason why I decided to translate this the building, just to have them separated here. So this is a pretty nice feature to do a comparison on different models. Okay. Okay. Now they look perfectly the same. Now let's make sure also the result is the same. So let's select the second fiber. Let's show the nodes. I think we have a problem in the internet connection. Okay, it's fine now. Let's show the nodes so that now I can go here, select it, and I can extract chart data from here. So we want to extract chart data on nodes. Now this time pay attention because by default it is selecting one of the databases, but we want to extract data on the second one database, okay? Stage number 2, and still displacement along the x-direction versus pseudo time step. Next, next, and we call it UF lamp finite length. And in this case, we don't need a new chart because we are going to use the previous one. So let's take this one and add the second one. Okay, now as you can see, the response is perfectly matching because we did the correction of the elastic stiffness in the previous example as well. We were using the 35%. Of course, there are small differences, but they are negligible. Okay, so this is the response with the finite length lamp plasticity. And now we are going to do the same for the spring-based lamp plasticity model. So let me go back to the preprocessor, save this file, and save it with another name. So save as, in this case, we want to save it as building not zero length. Okay, perfect. Okay, now let me move this one for the same reason I did it before, so that it does not overlap. So select everything and I choose move from here down here. Okay. Once again, let's make sure the local. Okay, now I want to show you the difference here. I keep this local axis inverted. It happened before, but as I said, it is not important to orient them because the global result will be the same. Now I keep it as it is now, and you will see that the global results will be fine with the rotational spring. But the rotational spring will show a different sign here. So same value as in the other columns, but with the opposite sign. This is just a sign convention that is used in OpenSys for the zero length elements. So I will show you and I will show you how to fix it, okay? So for the moment, let's keep it as it is. Let me switch the local axis off. And let's go in property. So now we are going to do the same change we did before. Now, before I forget, let me change the name of this one. I don't want to erroneously delete the previous database. And so we're at zero length here in the output database. Okay. We just need one change here because if you want to export the result on the zero length, we need also to ask for material stress and material strain because the zero length does not accept the keyword section fiber because it does not have any fiber. Instead, if you want to see the section force and deformation of a zero length, you need material dot stress or material dot strain. Okay, now let's go back to the material definitions. Now for the columns, we don't need the beam section property like this one, the hinged beam. We need, sorry, the beam with hinges, we need the hinged beam. So it is fine that we have the stiff material here because we will create the connection between the zero length in the connected degrees of freedom. It is fine that we have the elastic section. What we need is the uniaxial material for the plastic hinge. So add, let's call it moment rotation hinge uniaxial. And as we did before, we choose materials, uniaxial, others, modified environment in Winkler, pinching. Okay, now this is the same values we used before. So 3.93, 13. So the same values you have on the Excel file. 0.000189. Same in compression. Then the strength is 3.3 E8. And same but with different sign compression. Then few parameters for the cyclic response 0.4, 0.4, 0.1 the parameter of pinching. Then all the other values are fine. And then the plastic rotations. This one is 0.007, 579. Same in compression. And then the plastic rotation. I think we have a question. No. Oh, yeah. See in chat. Question 1. If I would like to perform a series of analysis, I didn't. Yes, names multiple space over STKO, yes. So for the first question, now you have to create different different scripts. In this case, if you don't want to create your own Tcl scripts, you need to create many analysis steps. And I know this is very cumbersome, of course, but the nice feature of STKO is that let me finish just a second this one so that I can show you how you can create a Tickle script. Just a second. So let me finish this one so I don't have to re-input all the parameters. 0.525. Okay. And the residual is 0.01, 1.05, 100, and 100. Okay, so this is fine. Okay, now back to question number one. If you don't want to create many analysis steps as I did here, because maybe you have to create hundreds of them, you can always create a Tickle file. Like you go here, this command, custom command. This custom command is actually a Tickle file. So you go here, and here you write any Tickle file that you want. Okay. So whenever you want to do something that is not available in STKO, use the Tickle script. Of course, you need to know how Tickle scripting works. However, I think in the near future we are going to add some features to do this kind of series of analysis for different ground motions and so on, parametric analysis basically. But at the moment, you need to use the Tickle script. And keep in mind that it is better to use the Tickle script rather than creating the script from here and modifying it by hand. Because if you modify it by hand, then when you regenerate the STKO file, your modification will be lost. Instead, if you create a Tickle script right here, your Tickle script will remain inside the SCD file. With STKO, you may use different many processor, yes, but you need OpenSysMP. As you can see here, you have the number of processor. So basically, in this example, the STKO that you download from the website, you only have the standard kit, which is the OpenSys sequential. Now, of course, if you are able to compile OpenSysMP, because now we cannot redistribute it, but probably for the next months, we will redistribute also the OpenSysMP. I have it here on my computer. If you have OpenSysMP, of course you can use multiple processors. Probably I will do a webinar on this, but basically you can have either OpenSysSP, like in this case. In OpenSysSP, you do a model like I did now, and you just choose the number of processors here. If instead you want to do parametric analysis or using OpenSysMP, you need OpenSysMP, and you need to create a partition, if your model is very large, inside the mesh. Okay, so yes, you can use STKO with multiple processors, but at the moment you need to have your own parallel version of OpenSys because we are going to distribute it in the next months. We need to fix some things about the licensing things about. Okay, so let's go back to the example. Property. I just created the engine Excel model. Let me see if it is fine. Just a check before running the analysis. Okay, it's fine. So this one is the uniaxial model for the column, and let's bring it before the column property. Now we need to create the property for the zero length as we did before. So moment rotation hinge zero length material. And as I did before, we go under special purpose zero length material. We choose 3D, 6 degrees of freedom. We use all of them. And we use the rotational spring about the Z local axis, and all the others are continuous, so stiff material. Stiff and stiff. Okay. Also, this one should be moved before. Okay, like this. It should be before the column property, but after the hinge one. Otherwise, you cannot reference this one here. Okay, now we go to the column property and we change it as we did before. Now, instead of being a force-based beam element, we go under where it is hinged beam physical property, and we choose the physical property for the inner element, which is the elastic section at 35%, and then we choose the moment rotation hinge at both ends. Okay. So now this one is automatically assigned, as you can see here. It was already assigned, we just changed the element type. And this is very convenient, as I said before. This element was continuously connected to the other, and now it has hinges. So there is no need for you to create these hinges manually. Now, of course, we need to do the same modification here. We first need an elastic beam, elastic element, as I explained before. So you go under beam column element and you choose the elastic beam column. You just need to say that it is 3D. Okay. And then we already have element for zero length, so we just need to create a beam element plus hinges. So we go here, we choose heat special purpose, hinged beam, and we choose the elastic element in the middle, not the beam element because this one is non-linear. So the elastic element and the zero length element, the same that we used for the beams, it is the same. For the two ends. So we press OK, and now we select all the columns by selecting either from here, if you want to select them manually, or you can select them using the property that you assigned. So you can select. Now you have all the geometries with this property assigned, already selected, and now you just drag and drop this new property here. Perfect. Now we don't need to change anything else. If we made everything correct, this one should just run. So just mesh it and run the analysis. Okay, now we'll show you that the global response will be fine, but actually the sign of only this hinge here at this corner node will have an opposite sign, and I will explain you why. It's just a matter of convention. So we press OK, back to the post processor, and now we load the third database, which is the zero length. Okay, it is here. Let me create another plot. Now, in this case, we don't want to create a fiber plot. We want a Gauss plot because we want to see the results on the zero length, which does not have fibers. So you can see the Gauss plot. Okay, so if in the Gauss plot we choose, instead of section force deformation, we choose material strain, what we see is the strain on the hinge. And in this case, we need to choose this the 6 degree of freedom. Now, unfortunately, as you can see here, it looks like a stress tensor, but it is not. It's just because OpenSys call it strain. It has 6 components, and STKO thinks that it is a stress tensor because the stress tensor in 3D has 3 components, but it is not a problem. So this one is the 6th component, which is the rotation about the local z-axis. Now, as you can see, all of them are red, except from this one. This one is blue. It has the same value. Let me synchronize all the plots and go to the very end of the analysis. Okay. It has the same value, which is basically the one that we have for the curvature times the zero length, but where it is, okay, the same value, but with a different sign. Now, let's first see that the global response is fine. So this is just a matter of sign convention. So let me go to the Gauss plot. Let's show the nodes. So I can select this one. And we are going to extract the chart data as we did before. So on nodes, stage number 2, and database of the zero length. Displacement versus pseudo time step. Next, next, and this one we call it zero length. We don't want to create a chart, as we did before. We used this other one, and we have the zero length, and as you can see, it perfectly matches. Okay, of course, with the difference of being a multilinear response rather than a continuous response. But then you will say, so why this one has a different sign? Well, it was just because, as I said, when we moved the geometry, or when you create it, you may have different orientation. Okay. Now the sign of the deformation in the zero length depends on the order of the elements, the order in which the nodes are assigned to the element. In fact, if I simply reverse the connectivity of this element, okay, now of course I need to remesh it and analyze it. you will see that the global response is still fine, but all the zero length have the same sign. As I said, this is not important, but it is nice to have the same convention. Otherwise, it becomes a mess to understand what's going on in your model. So let's go to the post processor and reload the old one. Okay, now they are all red, same color. Okay, and the result is obviously the same, didn't change. So it's just a matter of convention. So up to here is fine. You have seen how to change a model made with distributed plasticity, fiber cross-section, into two versions of lump plasticity. One with finite length, with the advantages of taking into account the bending, and bending axial interaction, with the slight advantages of having less calculation to do in the element here. But of course, the lump plasticity with phenomenological springs are even faster, but they don't take into account any coupling, either between the bending responses and neither between the bending and axial response. So of course you need to use this one if you need very performant analysis, because you have to do a quite large model, and if you think that there will be no coupling between bending and axial stresses. For example, when you expect axial stresses not to change too much during the analysis. Now, of course, we could have done the same for the beams, but I didn't have time. It's already 1 hour and a half now. Well, of course, you can repeat the same steps for the beams. As you've seen, it is very easy. You don't need to replicate the nodes. You can change from one element to the other without changing the geometry. This is the nice thing. So you keep the same geometry and you just change material properties or element properties and you're done. Okay? So if you have any question before we finish this webinar. So first of all, thank you for joining this webinar. And you can see on the website, we have many other webinars scheduled. And we already probably you received some emails asking you to fill a doodle where you want to choose what is the topic for the next webinar. So you can propose your own topics if you want. So if someone has some question, please. Is it everything clear? Okay, so let me stop sharing. If there is no further question, I will stop this webinar. So thank you to everyone and see you for the next webinar. I think we have, okay, no, I thought we have another message. Oh, okay. Can you please repeat once more, just a second? You said that you have defined two nodes at least while defining connectivity between elements. Or was it just to assign releases? No, let me share my screen. Okay, let me share the screen. What I was saying is that in the preprocessor here, as you can see, let me switch off the local access. Now, when you want to do, now imagine that you have to do this model in OpenSys manually. This node will not be just one node. In this position here, you will have one node for the bottom column and one node for the beams. And then you connect them manually with the zero length, okay? Now this is very cumbersome because it takes a lot of time to draw those duplicated nodes, and it is a mess if you have to do a very large model. Now in STKO you don't need to do this. You just create a single node here, and in fact if I try to select, let me move this one, just a second. If I try to select this node here, you will see that it doesn't ask me for overlapping nodes. I just have, well, here I have two edges, but this one is just one single node in STKO. Then, if I use the standard distributed approach, this one will be just a single node as usual. So all three elements share the same node. But if I use an hinged beam, STKO will automatically create an extra node here, but just when STKO is writing the Tcode file. So it will create an extra node, and it will assign the element to the interior nodes created on the fly by STKO. And then it will create the zero length for either for releases or for plastic hinges. So the advantage is that you don't need to duplicate nodes in coinciding position. This is the main difference. Okay, so here you have only one node. If we go on the post processor or whatever, let me switch off the beam extrusion so we can select the node. Okay, and let me switch off the beam extrusion also here. Now if I try to select, and I want to change also this one to Gauss point plot is the same, or the surface color map, but using the previous database map. Okay. And also for this one, I switch off the beam extrusion. Okay, and let me show the nodes. Now, if I select here like this, it will say, okay, what node do you want? Well, in this case, I have two nodes for the beams because they were released, and just one node for the columns here. Now, in the other case, let me change it. Let me create another one. Surface color map here. Switch off the beam extrusion. I switch on the nodes, and then I try to select and zero length. Okay. I try to select this one. Now in this case, I have four nodes, one more than here, because here I had releases on the beams. So while in STKO, I had only just one node. Here I have three nodes here, the joint node, which is connected to the beam, and two extra nodes for the releases on the beam. Now in this case, also the column as a release with respect to the corner nodes. And in fact, I see four nodes, four coinciding nodes. So this is basically the difference. While in STKO you draw everything connected, the OpenSys model has automatically these nodes disconnected and joined with a zero length element. Okay, so let me go back to the questions. Okay. Is there any other question? So if not, thank you very much and see you to the next webinar. Next webinar will be on soil structure interaction. And then we will be once again back to the masonry micromodeling. So thank you everyone. Let me